In this video, we are going to start talking about cell potential. And the cell potential is going to depend on the difference in electrical potential between two different electrodes. And I have here a table of cell potentials. So you'll notice that hydrogen, this is all built off hydrogen, which is in the middle with an electropotential of 0. And then from there, they get more negative or more positive. Keep in mind the tables might be flipped where the negative numbers are down here and the positive numbers are down here, but they still give the exact same information. The more positive it is, the better oxidizing agent it's going to be. The more negative it is, the better the reducing agent. So we can use this in order to calculate the cell potential, and we can use the cell potential to determine whether a redox reaction is spontaneous or not. So we have the equation E cell is equal to E cathode minus E anode. For spontaneous processes, E cell must be positive in order to be spontaneous. So we looked at the galvanic cell between zinc and copper. So we had solid zinc plus copper goes to aqueous zinc plus solid copper. And in this case, we found out that zinc is being oxidized, it loses electrons, and copper is being reduced, it gains electrons. So we can calculate E cell for this process. Since zinc is being oxidized, it is at the anode, and since copper is being reduced, it is at the cathode. So I can go and find the cell potential of zinc and copper. So it looks like I have zinc right here and copper right here. So I can plug that into my E cell equation. Remember, it's E cathode minus E anode. So my copper is going to go first. We have 0.40 minus the anode, which is zinc, negative 0.76. And when we do that, you can see we get 1.16 electron volts. This is a positive process. So it is a spontaneous process. Let's look at another example, because now we can use this to predict whether a process will be spontaneous or not. So let's see how we can make a spontaneous process out of tin 2 and silver. So the first thing I want to do is look up what the cell potential for tin and silver are. So tin I have right here, negative 0.14, and then silver I have down here, positive 0.80. So I'm going to write those two processes out. We have tin, 2 plus 2 electrons yields solid tin. And you'll notice that these equations are all showing the reduction half cell. All right, so keep that in mind. And my E cell for the tin is equal to negative 0.14. If I look at the silver, it was 0.8. And you'll notice that this can be units of either electron volts or volts. So if I plug this into my equation, and I put tin first, followed by the silver, that gives me a negative 0.94 volts. Now if I swap them, I can put silver first minus the negative 0.14. That gives me the positive number. So this one here is spontaneous. And since I know the first number represents the cathode and the second number represents the anode, this tells me what is being oxidized and what is being reduced in this process. So I look at the equation and I can find the point A is at cathode, silver is 0.8, so that means silver has to be at the cathode in order to get a positive number. So silver is going to be reduced, and that also means that silver is the oxidizing agent. Now, in order to get a positive number, tin has to be at the anode. So that tells me that the tin is oxidized. That also tells me that tin is the oxidizing agent. All right, now something that people get a little bit confused about is you still have to get a balanced chemical equation. You'll notice that with tin, we have 2 electrons, but silver only has 1. Since silver is at the cathode and being reduced, I know that I can list it as Ag plus 1 electron will yield Ag solid. Since tin is at the anode and being oxidized, I'm going to have to flip this equation right here because remember, this is the reduction and we need to show the oxidation. So when I flip that, I'll get the solid tin and that will yield solid silver plus our tin 2 ion. So if you were just to look at this, you might not be able to tell that it's not balanced. But when we look at our electrons, we can see it's not balanced, and I need to multiply this equation by 2 in order to get my balanced electrons. So that means I'm going to have a 2 here and a 2 here, and there'll be a total of 2 moles of electrons being transferred. So now we can relate the free energy and the electrical energy. So that is looking at delta G and E cell. So delta G is equal to negative NF E cell. So this is how we can relate those two equations. I will give you this equation, but you need to know how to use it. N is the number of moles of electrons. And those electrons are being transferred. So we just calculated that for our previous equation, N was equal to 2. F is Faraday's constant. Whoa. And Faraday's constant is equal to 9.65 times 10 to the 4 joules per moles of electrons times volts. So if we were to look at our previous example with the tin and silver, we could calculate delta G for this process. And we just calculated E cell for that process, and it was equal to 0.94. We also know that the number of moles was equal to 2 moles of electrons transferred. So I can calculate delta G. We'd get negative 2, put it in for N, times Faraday's constant, times our 0.94 volts. And when you do that calculation, it will give you delta G for this process. I hope you can see that the delta G that you get for this process is going to be negative. That goes in line with our stuff we already know about spontaneity. If delta G is negative, it's going to be spontaneous. And we already calculated E cell and found out it was spontaneous. So we can also, I meant to tell you, if you tell me what this is equal to in class on Tuesday, I will give you extra credit if you are correct. All right, we can also relate the free energy, E cell, and K. So E cell is equal to RT over NF times the natural log of K. And here, R is going to be equal to the 8.314 joules per mole times Kelvin. Now, something you need to be aware of is a lot of textbooks will give this equation in its alternate form, where we have E cell is equal to 0.0592 volts over N times the log of Q. Now, something you need to be aware of is this always assumes that your temperature is at 25 degrees Celsius, and it only gives you 3 sig figs. So it's not the best equation to use. Sorry, this should be K. We'll get to Q in just a minute. It's not the best equation to use if you're not at 25 degrees Celsius and if you don't want to limit your sig figs to 3 sig figs. So I like to look at this and see how we can connect all three of these values. So if I put delta G at the top here, I can convert between delta G and K by using the equation delta G is equal to negative RT natural log of K, which we learned about when we talked about thermodynamics. And then I can go between delta G and E cell using delta G is equal to negative NF E cell. And then I can go between E cell and K using what we just learned. E cell is equal to RT over NF natural log of K. Now, if you are not at a standard state, we can still calculate our cell potential using what is called the Nernst equation. So E cell is going to be equal to the standard E cell minus RT over NF natural log of Q. So another way to represent this, if you want to take out the constants, is you would still have E cell minus 0.0592 volts over your moles of electrons times the log of Q. Notice that when we use that constant 0.0592, it changes to a log, and it is not a natural log anymore. All right, so what we can do in class on Wednesday is go through a bunch of problems get some practice on how to use these equations.